You haven't been able to hear me talking this entire goddamn time. All right. Valence shell, electron pair, repulsion. This stuff builds directly on Lewis structures. If you can't do Lewis structures, you're not going to be able to do this. VSEPR, valence shell electron pair repulsion, means that electrons are going to get as far away from one another as possible. Valence shell, because that is the electrons. That's where the electrons involved in the bonds are. Electron pair, because the electrons are always paired up in these things, and repulsion because negative charges they aren't. AudioStream's current bit rate is lower than the recommend. Can you still not hear me? My mic is now working. Let's see. What's the audio bit rate? Well, I can't. I'm not going to worry about that right now. All right. Well, he's on the other side of the room, but you can still hear him chewing his bone. Okay, so, okay, you can hear me. Good. All right, so that means that you get these electron domains. Okay, an electron domain is just a place where electron lives. They can also be called electron groups. I'm not sure which they went with in the lab videos that we have over here. But it's just a place where electrons live. So one domain would be either one bond or one lone pair. Okay? And a bond could be either a single bond, a double bond, or a triple bond. It doesn't matter how many bonds there are. It still counts as one electron domain. So those electron domains then get as far apart from one another as possible around the atom. So if you have two electron domains, they just go to opposite sides of the atom. And then, of course, people have done a lot of math to look at the complex 3D geometries necessary in order to get the electron domains as far apart from one another as possible. So you can have different numbers of domains depending on, what the actual Lewis structure of your atom is. So we go from 2 to 6. If you have two domains, then you're going to end up with a linear geometry. Okay? We already saw that with the previous page. Just your atom in the middle, electron domain goes out to either side. With 3 electron domains, you get what's known as trigonal planar. Okay? That means that it is, when you look at it, it is a flat triangle. If you were to look at it edge on, it would just be a flat line, okay, because it's a triangle. What that means is that you have your domain, then one group goes up, one goes down and left, the other one goes down and right, making your triangle. With 4 electron domains, we break out of 2 dimensions and we go to a 3-dimensional shape, and it is known as tetrahedral. Okay. So a tetrahedron is one of those ideal structures that the ancient Greeks thought made up the universe. And it is a pyramid where all 4 sides are equilateral triangles. So this is not your traditional Egyptian pyramid. It doesn't have a square base. It has a triangular base. So the atom would be at the center of this tetrahedron, and then the 4 electron domains point to the 4 corners of the tetrahedron. So when we draw this in 3 dimensions, we draw it like this. One points up, one points down and left. The other 2 have to break out of the page. Okay? So a straight line just means that it lies directly in the same plane as the page. Okay? A triangular wedge like this means that it's coming out of the page towards you. And this dashed line back here means it's going back out of the page away from you. So that is how you get your tetrahedral geometry. So that right there, the dot is the center of the tetrahedron. One domain goes straight up to the top. One is going down and to the left. One is coming down, right, and forward. One is going down, right, and backward. And that's your tetrahedral geometry. And then for our 5 domains, we get a bit of a change. It is trigonal bipyramidal. Okay. In this case, we're going to have 2 triangular pyramids. They are going to be butt to butt. So now we have one going straight up, one coming straight down, one going straight to the left, and then like that. Okay. So if you were to look at this thing from the top, you would just see a triangle. Okay. You'd have one going left, one like that, one like that. Because then the 2 going above and below would just be going in and out of the page directly. So trigonal bipyramidal because you have 2 triangular pyramids butt to butt. Finally, we have 6 electron domains. This is called octahedral, okay, because it forms an octahedron. And finally, we have our Egyptian pyramid, where you have 2 square-based pyramids butt to butt. Okay. Okay. And it's called octahedral because when you link this up, you have Okay, Sharpie is not going to cut it for this, I don't think. But you end up with an octahedron shape. If I knew where my dice were, I could pull out one of those to show you, because an 8-sided die is an octahedron. Actually, I can probably do a quick bit of Googling. But, this is what it looks like. Yes, there we go, octahedron. So you can see here, oops, I'm covering it up with the thing. Boom. Okay, so you can see here the 2 square-based pyramids, oops, dang it, right on top of each other. Okay. The atom would go at the center. One bond goes straight up to the top, the other bond goes straight down toward the bottom. The other 4 bonds go to the 4 corners of the square in the middle. All right. So those are the 4 basic shapes, okay? And then we modify those based on how many of those electron domains are non-bonding pairs. But first, we have to talk about bond angles. Bond angles are one of the things that you need to know about. So when we talk bond angle, we're talking going from group A through the atom in the middle, then to group C. Okay, so that bond angle right here for a linear molecule is just a nice straight line. It's 180 degrees. Okay. For a trigonal planar molecule, we're talking about this angle right here because it's inside a nice equilateral triangle, one of those perfectly symmetrical triangles. It's 120 degrees. For tetrahedral, it's a bit weirder. It is 109.5 degrees. When we get to the trigonal bipyramidal, or trig-bippy, we have 2 sets of bond angles. This is the only molecule for which this is the case. Okay, we have 90 degrees going from what's called polar to equatorial. That is to say we have a north pole and a south pole, and then we have 3 guys going around the equator. So going from polar to the atom in the middle to the equator is 90 degrees. Going from 2 on the equator, from equator to atom to equator, that right there, you're going, that's just a nice perfect triangle there in the middle, so it's 120 degrees. And then coming back to the octahedral, these guys are nice and regular, just a lot of 90-degree angles. So you can see, as we pack more electron domains around here, it starts to get more and more crowded. Okay, the bond angles just get smaller. So 180, 120, 109.5, then a mixed 90 and 120, and then finally just plain 90. So those are the 5 basic shapes that you're going to have to memorize. And yes, you will have to memorize them. You're not going to get any sort of chart for any of the tests with these names or bond angles or anything like that on there. All right, so how do we modify these? Okay. These basic shapes are assuming that all of your electron domains are single bonds, basically. the simplest way to alter these is by, changing some of them to non-bonding pairs. So we'll start with 3. Okay, so if it had 0 non-bonding pairs, or sorry, 0 lone pairs, they called them. 0 lone pairs is trigonal planar, but if you have 1 lone pair, then what you do is you replace one of those lines with nothing. See, when we look at the molecule, we can see the bonds, we can see the atoms, I should say. We can't see the lone pairs. So the geometry changes to this. Okay, so the electron domain is still there. The non-bonding pair, or the lone pair, is still present, but we can't see it. It still makes its effect felt. Okay, it still alters the geometry. So we make the distinction between the electron domain geometry, which is just going to be the trigonal planar, the number of the number of electron domains, and between the molecular geometry, which is when you take into account that non-bonding pairs or lone pairs are invisible. So, with 3 electron domains, if 0 of them are lone pairs, it's trigonal planar. If one of them is a lone pair, then it is called bent. Okay. It's nothing fancy, it's just a bent geometry. And now the bond angle has changed slightly. It is less than 120 degrees. See, lone pairs take up more space. So the atoms, the bonds, get squished together. So it's just going to be less than 120. How much less than 120? That would depend on the molecules. They don't ask anything exact. You just have to say less. So 4 and 0 is tetrahedral. And we're going to have 2 possibilities. We can have 1 lone pair or 2 lone pairs. So if you have 1 lone pair, then it looks like this. Remember, the basic geometry is the triangle-based pyramid. And so now the one that's up top is gone. Okay. Honestly, it could have been any of them. These 4 are identical, but we choose the one on top because this lets us see that now we have a squashed looking pyramid. Okay, one going down and left, one going down and right and forward, one going down, right, and back. So this geometry is called trigonal pyramidal. Okay, it is no longer called tetrahedral. I mean, the electron domain geometry is still going to be tetrahedral, but the molecular geometry is trigonal pyramidal. And once again, the bond angle has changed. It is now less than 109.5 degrees. Then if we have 2 electron domains, another one of these guys becomes invisible, and we end up with another bent geometry. But it's a different bent geometry. It's important to make these distinctions because, again, this bond angle is less than 109.5. Okay? So it's going to have a different shape from this guy up here. This has 120 degrees. This is 109.5. So if I were to include the invisible whatchamathings, then you would have 1 electron domain up top like that, making its presence felt, pushing down. And here you would have 2 electron domains up top, pushing down, making their presence felt. So, continuing. 5 electron domains. 5 and 0 is trigonal bipyramidal. Hopefully you won't mind me abbreviating a bit with this geometry. If you have 1, you remove one of them. Now it looks like this. Okay. So with all the other geometries, any position is exactly the same. But with trigonal bipyramidal, you have the choice, polar or equatorial. And if you're at the North Pole, say, and you look around yourself, you see 3 neighbors at 90 degrees. You can it has 3 immediate neighbors, one at 90. Each of them is at 90 degrees, the 3 equatorial guys. But if you look at the equatorial ones, it has 4 neighbors, 2 at 90 degrees, 2 at 120 degrees. So the lone pair is always going to go equatorial, because having 2 neighbors at 120 degrees is preferable to having the additional neighbor at 90 degrees. Okay. Either way, you have 2 neighbors at 90 degrees. The question is are these 2 equatorial neighbors? So that's why that lone pair goes equatorial. The technical name for this is called disphenoidal, which I like just because I like funny words. But everybody and his kid sister instead calls this a seesaw shape, because you put it on its side, it looks like a seesaw or a teeter-totter. Okay. So again, the bond angles have changed. You now have less than 90 degrees, less than 120 degrees. Because again, the the lone pair is squishing the other atoms together. All right. If you put a second lone pair on there, it will also go equatorial. And you're going to be left with this guy, which is given the fancy name of T-shaped. So that is a T-shaped geometry. And the bond angles are just less than 90 degrees. Okay. You don't have to worry about the 120 degrees anymore, because the 2 equatorial guys that would cause that are gone. They're vanished. They disappeared because they're both lone pairs. And finally, if we have 3 lone pairs, the third one will also go equatorial, and you'll just end up back here with another linear geometry. And now, because those 3 lone pairs are all perfectly evenly spaced around the equator, we've re-achieved a nice simple geometry with a nice straightforward 180 degrees. Okay, nothing is the lone pairs would be squishing, but they're all squishing equally, so nothing is warped, nothing is shifted or bent or changed like that. So just a nice even 180 degrees. And finally, we get to octahedral. Okay, so if we have 0 on the octahedron, on this guy, it's octahedral. And it has this shape, like the 3 axes of a 3-dimensional graph, x, y, and z. So once again, all directions are equivalent. We can pick any of them. Okay, so the first one, we just go ahead and take the one off the bottom, and we end up with this shape, which is square pyramidal. This is the nice, wonderful Egyptian pyramid. Okay. It is nice and even. Once again, the non-bonding pair or lone pair is squishing things. So technically the bond angles are going to be less than 90 degrees, but you have 5 of these guys pushing back, so it's a very small amount of deviation. Next up, we have 2 lone pairs. Now these 5, the positions are not all equivalent. We want to get the lone pairs as far apart as possible, so the next one goes on the opposite side. Okay. So this is now square planar. Okay, it's just a perfectly flat square. And because the electron domains are on opposite sides of this atom, the squishing is perfectly equal, so it's exactly 90 degrees again. Next up, if we remove 3, we would end up with another T shape. And it's going to look very, very similar to the octahedral one, but that's not much we can do about that. It's going to be less than 90 degrees. Once again, we got squishing. And finally, if we have 4 lone pairs, then we are back to linear again. Okay. And once again, those 4 lone pairs are all squishing equally, and we're at a nice even 180 degrees. So those are your geometries. Okay. So if you have 0 lone pairs, then the electron domain geometry and the molecular geometry are exactly equal. But if you do have lone pairs, then the molecular geometry is going to be different from the electron domain geometry. Okay. So let's see if I can squeeze all of this onto one page using Sharpies. It's going to be difficult. Wish me luck. Okay, so number of electron domains, number of lone pairs, geometry, angles, shape. Okay, so we have 2 electron domains, 0 lone pairs. That is linear. It has 180 degrees, and it is just that guy right there. 3 and 0 is trig planar, 120 degrees. 3 and 1 is bent, less than 120, and it looks like this. 4 and 0 is tetrahedral, 109.5. 4 and 1 is trigonal pyramidal, less than 109.5. 4 and 2 is bent, less than 109.5. Looks like that. Doesn't look like I'm going to make it. 5 and 0, trigonal bipyramidal, 90 and 120. 5 and 1, seesaw, less than 90, less than 120. 5 and 2 is a T-shape, less than 90. 5 and 3 is linear, 180. I was kind of hoping I could get it all on one page. I will cheat. 6, 0, 1, 2, 3, 4. Octahedral. Let's see. Square pyramidal. Square planar. T and linear. 90. Less than 90. 90, less than 90, 180. And then I just won't draw the geometries for that one because there's no way I can get them all in there. All right. Now, just remember that the electron domain geometry is always going to be identical to the molecular geometry when there are 0 lone pairs. And then when you add lone pairs, that's when the molecular geometries start to change. All right. So this is pretty much what you have to memorize. Don't worry if you can't really read what I have written here. This chart is available everywhere. It is in the textbook. You can find various versions of it online and things like that. So all you have to do is draw the Lewis structure and count the number of electron domains. And remember that an electron domain is any bond, whether single, double, or triple, or a lone pair. Okay. So now let's talk about polarity. So let's see. Back to good old this guy. All right. So if you're looking at a covalent compound, okay, you're looking at covalent bonds, the elements or the atoms on either end of that bond can have different electronegativities. If they do have different electronegativities, that means you have a polar bond. If they have the same electronegativity, or if they're very, very close, then you have a nonpolar bond. Okay? So technically, it can go from 0 to, I believe, 0.4, and we call that nonpolar. Then from 0.4 to 1.7 is going to be polar covalent. Greater than 1.7 is going to be an ionic bond. Okay. The thing is, unless they give you electronegativity charts, you're not going to be able to calculate these numbers. So it's just, instead, you use a rule of thumb. Essentially, nonpolar is going to be if the two atoms on either end of the bond are the same element or carbon and hydrogen. Okay. If they're the same element, it's a nonpolar bond. If they are carbon and hydrogen, it's a nonpolar bond, because carbon and hydrogen are very close in electronegativity. Now, there are other elements out there that could also give you a 0 to 0.4, but the only one that I would expect you to remember is carbon and hydrogen. Polar covalent means that they are different elements except for carbon and hydrogen. And finally, ionic bond would be metal plus a nonmetal. So polar covalent, technically different elements, but they're both nonmetals. Ionic compound, metal plus a nonmetal. And again, you can get all sorts of things that would actually, change this up and, play around with these things. But these are the rules of thumb, just the basics that you should know. So what does polarity mean? It means that you have an unequal sharing of your electrons, such that, for example, if you look at carbon dioxide, carbon is bound to oxygen. Oxygen is very electronegative. Carbon is less electronegative. So the electrons of the bond spend more time over here with oxygen than they do with carbon. So that's what gives you a polar bond. And we represent that with this guy right here. Okay? That just an arrow showing that we have it pointing along the bond from the positive toward the negative. Okay? And then we just draw the little hash line there to make it look like a plus sign at the positive end of the bond. Another way of representing that is with this. Okay. These swoopy looking things, those are another way of doing the letter D, as in delta, as in difference. This is kind of a cursive lowercase Greek letter delta. So delta plus, this means that we have a partial positive charge on the carbon because of the unequal sharing. The electrons are spending more time over here. And we have a partial negative charge in the oxygen because the electrons are spending more time over there. Now, the other bond does the exact same thing. So we get that guy, okay? Which means you also get a partial negative charge on this oxygen. Now, polar bonds, those are very, very common. But you can have a polar bond inside of a nonpolar molecule. These two oxygens are on opposite sides of the compound, so they're pulling in exactly opposite directions. So it's like a perfectly matched tug of war. They perfectly cancel each other out. Okay? Which means that even though you have polar bonds, you have a nonpolar molecule. In order to have a polar molecule, you need two things. Not just polar bonds, you also need some form of broken symmetry. You need an unevenness to the molecule. So, going back to these geometries here, if you have 0 lone pairs, that will always give you a nicely symmetrical molecule. So 0 lone pairs here, just like with carbon dioxide, okay, you get a perfectly matched tug of war. 3 and 0, trigonal planar. it's more complicated. It's a two-dimensional tug of war, but it's still perfectly matched. This guy pulls up, this one pulls down and left, this one pulls down and right. The left and the right perfectly balance each other out. And then their downward pull perfectly balances out the upward pull from that guy. But when you get to 3 and 1, suddenly this guy up top has disappeared. These two are pulling in the same direction. So you have lost that symmetry. You've got an unevenness in the molecule. So we can add a final column here. Squeeze it in, polar or nonpolar. Okay. If all of your atoms are the same, this is only true for all of the atoms being the same, then will it be polar or not? This will be polar, these would be polar, these would be polar, and then finally square pyramidal would, T-shape would, and the others would not. Okay. Oops. This one is nonpolar. I made a mistake there. I wasn't thinking. I was trying to go too fast. Because we remove one lone pair, we have broken the symmetry on this Trigbippy. You remove a second lone pair, the symmetry is still broken. You have this guy pulling to the right with nobody on the opposite side. But this one, you remove the third lone pair, then you bring the symmetry back. So you end up, when you end up linear, the one pulling straight up, the one pulling straight down, they cancel each other out. Okay. And then for octahedral, it starts out nonpolar, same as always. You remove one, you end up square pyramidal with, the one on top not balanced out by anything else, so it's polar. You remove a second one, then you're just square planar, and it becomes nonpolar again. You remove a third, you end up T-shaped, polar. You remove a fourth, you end up linear, and it ends up being nonpolar again. So if all of your atoms are the same, then those are the rules for polar versus nonpolar. If your atoms are different, then anything can be polar. Okay? So for an example of that, let's look at formaldehyde. Okay. Formaldehyde is CH2O. Okay. You have carbon in the middle. It is double bonded to an oxygen and then bound to two hydrogen atoms down here. So you have 3 electron domains, 0 lone pairs. This is a trigonal planar geometry. But suddenly, but that does not mean that it's nonpolar, because this bond right here is very strongly polar, pulling up toward oxygen. These two bonds down here are nonpolar, okay? Because carbon is bound to hydrogen, and they have very similar, very close electronegativities. So another way is delta plus, delta minus, partial positive charge on carbon, partial negative charge on oxygen. And this molecule would be polar. Okay? So you're looking for both polar bonds and broken symmetry. Second M. Okay, you're just looking for any sort of unevenness in the molecule. And that means that it could be something like this, or it could be lone pairs. Now, if you're not good at thinking of 3 dimensions, this can be difficult. If you're looking at, say, a trigonal bipyramidal thing, which is why memorizing a chart like this is not the worst idea in the world. I know I'm fairly good at manipulating 3-dimensional stuff in my head, but I also know that I am weird. So don't assume that you have to be like me. Also, don't assume that you have to be able to just whip this out from memory at the same speed that I did. I've been doing this for a while. All right. So all of this stuff proceeds from Lewis structures. You draw your Lewis structure, count the number of electron domains, count the number of lone pairs, everything else follows from that. Okay, and I think that I have covered everything. They have some simulators for you to play with so that you can see molecular shapes molecular geometries so that you can see polarity, things like that. So I recommend that you definitely play around with these things. It might give you a good feel for the way these things work. Okay. All right, and unless there are any questions, I will be taking off. So I'll hold on for a little bit, see if you have any questions. All right, in that case, I will see you around. Oh, for the first time this coming week or the weekend.